All right, so this is question 2 or part 2 of essay number 1 for physiology. And we're gonna start out by talking about RMP, or resting membrane potential, and what that looks like. But before we get there, we're gonna use the same example that was used in our book. It explains why there is an RMP and how that affects the cell and the ions inside. And so we know we have a concentration gradient. We've talked about in class. We also have an electrical gradient. And so, like in the book, we're going to put an equal amount or an equal concentration of chloride and potassium into the solution. But this is 2 compartments, side A, side B, and there's a semi-permeable permeable membrane, but it's only permeable to potassium. It's not permeable to chloride. So we're going to put more of this solution on side B and less in side A. So let's see. Put our potassiums in. Put in our chlorides. Okay. So as you can see, a lot more on this side. So with this being the case, sodium and potassium are going to want to move down their concentration gradient to side A. But chloride's not permeable, so it's not going to be able to go through the membrane. But potassium is, so it's going to move down its concentration gradient, and we're going to start to see a few potassiums move down to this side. And it's moving down its, can't really see that, its concentration gradient that way. But as it moves down, it's leaving the chlorides, which are negative. It's leaving negatives in side B. So slowly, side B is becoming negative over here. This compartment's becoming negative altogether. And as these move over, this is going to increase in negativity. And over here, side A is going to increase in positivity. We have a bunch of positively charged potassiums. So positive, negative. This is where we have the electrical gradient come in. These potassiums aren't going to want to, they want to diffuse this way because of the concentration gradient, but then we remember we have the electrical gradient, and they're not going to want to diffuse anymore because it's negative over here. These positively charged potassiums are attracted to a negative, so they're not going to want to move over. They're going to come to a point where they're not going to want to go across this membrane anymore because they want to stay where it's negative. And that is the electrochemical gradient. We have the chemical gradients of chloride wanting to go this way because there's less concentration over here. We have potassium, which started over here as more, but it moved that way because it had less concentration. And it did that, but since the chlorides couldn't move, they were stuck over here. The potassiums could, but it left these chlorides that are negative, and and so it left this side, compartment B, to become more negative. And so we have potassiums leaving due to the concentration gradient, but we also have potassiums coming back through to this negatively charged side, because they're also attracted to this negative through their electrical gradient. So that's why within a cell, or within the body with the cell, and the ECF and inside the cell, the ICF, the cellular part has a negative charge. And it's due to the concentration gradient and the electrical gradient. So let's move over here. Let's see. Okay. So this is inside of our cell. This is the outside of the cell. This is our membrane. And we know that for resting membrane potential, it's at -70. And the things that contribute to that -70, there's 3 of them. There's the sodium potassium pump, which pumps 2 sodiums into the cell. Sorry, pumps 2 potassiums into the cell and pumps 3 sodiums out of the cell. And it does it through ATP. We also have potassium leak channels that allow potassium to move in or out. And it moves in or out, moves out due to the concentration gradient, and it moves in due to the electrical gradient. We'll talk a little bit more about that in a second. But also inside the cell, the biggest contributor to the -70 RMP is these negatively charged proteins. So, first we're going to talk concentration gradient. The sodium potassium pump creates this concentration gradient because it pumps potassium into the cell, putting more potassiums into the cell. It pumps sodium out of the cell, putting more sodiums on the outside of the cell. So it creates this concentration gradient of more potassiums inside the cell, so they want to go out the leak channel to the outside of the cell where there's less potassium. Sodium wants to do the opposite. There's more sodium on the outside, less sodium on the inside, so the sodium wants to come inside, but the sodium is less permeable. It has less vehicles to come back inside of the cell. So that's where our chemical gradient is established, is through the sodium potassium pump. And the sodium potassium pump contributes a little bit to this -70, but it's not a huge factor. But yeah, the potassium leak channel can let potassiums out due to the concentration gradient, but it also can let them back in when they want to come back in due to the electrical gradient. Kind of like what we talked about over here in our compartments. But let's see here. I want to make sure I'm not missing anything. Okay, let's talk about inerts and the driving force a little bit. I think this will help us explain more about the RMP. So we're gonna move back down this way. One sec. Chris, you can come in if you want. Okay, I love you. All right. So, the Nernst equation, we're going to use, this is the equation, it's E equals, it's supposed to be 61.5, but it's fine, over Z, which is the charge of the ion, times log 10, divided by the molecule inside the cell, molecule outside the cell. You can also write it like this, where this is negative 61.5 over Z log, and that's flipped, but this works too. So this is going to tell us At what point a certain molecule reaches its resting membrane potential. So for example, for potassium, it's markers. For potassium, it has 150 millimoles inside the cell and 5 outside the cell. So there's obviously a concentration gradient of it wanting to move out, but we also know that it still has that electrical gradient. So the Nernst equation helps us find at what voltage potassium is going to reach its like equilibrium. And the equilibrium is when we have the same amount of potassiums going from inside the cell to outside the cell due to the concentration gradient, to the same number of potassium coming inside the cell due to the electrical gradient. Remember over here we talked about with potassium and chloride, we started out with the concentration gradient, potassium wanting to move this way, but as it did that, it left behind negatively charged negative charges, which made this negative, which started to draw in potassiums because they're attracted to that negative side. So that's the same thing with inside the cell. The Nernst equation only takes into account one molecule. And so it gets that equilibrium for that single molecule. And then with the Nernst equation, we can figure out the driving force. And it can tell us more about the movement of that molecule. So let's figure this out real quick. Pretty much, you just plug this in, plug. I think that gets us, I want to say like 90. I think it gets us 90. The Nernst for potassium is about 90. And so when it hits 90 millivolts, that's when the net, that's when we have the same amount of potassiums coming in and out due to the electrical chemical gradient. The driving force is going to tell us more about that molecule and how it's going to react with the cell that it's in. So for this one, I think the book gave us an example of like a negative 80 millivolts, and this is like the membrane potential. And so we're just going to do that number minus this number. And so I think it's like 150. No, sorry. No, that's not right. It's like 170, I think. Negative 80 minus 90. Yeah, 170. So that's going to give us the driving force of 170 for potassium. And the driving force, hypothetically, we always put that inside the cell. So crap. Maybe 170. Is that it for it though? One sec. All right, I'm back. I had a little hiccup there. So yeah, this is right. This is like 90, 95. It's actually negative 95. That's why I was getting a positive number. So we're going to do negative 80 minus negative 90 or 95, and it's going to get us positive 15. We get positive 15 inside the cell. That's the driving force for potassium. And potassium, we know, is what? It's a positively charged cation. So if it's positive in here, it's not going to want to stay. It's going to want to be driven out. So that takes into account electrical gradient and the concentration gradient and puts it into the driving force. And it just tells us what this specific molecule is going to do, what direction it's going to go. So we know it starts on the inside, and so we know it's a positively charged cation. It's not going to want to stay with this positive, so it's going to want to go out of the cell. Let me sharpen up on this a little bit more, but that's why we're doing this. A little bit more. And the reason why this is at negative 70 is because it takes into account not only potassium, which is a negative 90 Nernst number, but it also takes into account sodium, it takes into account chloride. And yes, potassium has the biggest effect on it, but there's also sodium, calcium, and stuff. So it brings it up to negative 70 millivolts on the inside. It's a nice little picture I drew. Shows, I don't know why I drew this, but I think it was kind of just showing how there's more sodium on, some more potassium on the inside, more sodium on the outside. Kind of the similar thing I looked at over here, somewhere over there. But potassium is going to move out due to the to the chemical gradient. But then once it's moving out, it's going to leave behind negatively charged ions or negative charges. And so there's going to be it's going to become more negative, and then it's going to start bringing in these potassiums. And once they have the same amount going in, going out due to the electrical chemical gradient, that's when we hit equilibrium or RMP. So yeah, that's RMP. Let's also talk about action potentials. So we know that these neurons, they send signals through like the afferent and the efferent pathway. And so the way they send these signals is through these the axons and the neuron cells. But there has to be a charge that sends it through. And so the action potential is that charge that's being sent through the axon, either to the brain or back down to the effector. So this is a graph we use a lot in class. We're going to put negative 70, that's our RMP. Then we have this line, which is our threshold. And the threshold's important because that's where our action potential begins. But I'm going to draw something. Okay. This is an action potential. So usually with the cell, the only channels that are being used when in resting membrane potential, we talked about sodium leak channel. Let's talk about ATP, sodium potassium pump. We talked about, I think that's mostly we talked about. So that's what establishes the RMP. And then we have a graded potential where this gets a little positive, and sometimes we can get a little positive and then go back down to RMP. The graded potential is like a stimulus, and that's when something opens up these different channels that are either ligand gated channels, or they can be like mechanical channels. Like if there's pressure on the cell, these things will open. And so in this point in time, it's just sodium, it's just potassium leak channels. And then here, at number 2, there's like these ligand gated channels, or the mechanical channels open due to like a stimulus. And when these open, it gets more positive. But then here at number 3, this is where it hits the threshold. If it gets to number 3, the threshold, will do an action potential. But in this case, there is I actually hit a drone up here, but I erased it. You can have a channel that's a sodium voltage gated channel. It has a gate, and then it has a little inhibitor. It also has a spring on it that allows this door to open or not. And this spring is calcium, and the more calcium you have, the more difficult it is to open this gate. The less amount of calcium you have, the easier it is to open the gate. So at this point, let's say one of these mechanical gated channels is potassium, or something that comes into the cell, and the way these voltage gated channels open, it's due to a change in like the separative charge of the membrane. And so if something comes in, let's say it like changes this chemical charge separation, it's going to affect this spring. And if there's less negatives, it's going to affect the calciums and allow this spring to be open. And so when this opens, it's a sodium voltage gated channel. It's going to let in sodium to the inside of the cell. So the sodium is going to come in, and since sodium is positively charged, it's going to shoot up and become less negative or more positive, and that's called depolarization, when it moves away to threshold or away from this negative RMP. But then it's going to hit a point up here, 0.5, where this voltage gated channel is going to close. And the reason why it closes, it has like a little timer, and the timer is very quick. It has an inhibitor that flops down and blocks this. And so the only reason this blocks is because it's just made that way, and it has a timer, and that quick time goes through, it opens, lets sodium in, and that inhibitor comes down, closes on it. It's like clockwork. That's going to stop the sodium from coming in, so it's not going to get more positive. But also around this time, you're going to have a potassium gated channel that has a door, but it doesn't have an inhibitor, but it opens up very slowly. So during this whole time, it's still opening, but it's opening very slowly. And so if it's sodium leaving the cell. But like I said, it's not leaving super fast, and so it's still going in a positive direction because we have those positive sodiums coming in, positive potassiums going out. But it's opening slowly, so not a lot are getting out. But here at number 5, this thing closes, and then the potassium gate is fully open. So now positively charged potassium is leaving the cell because the cell is super positive, or a lot less negative, and so potassium wants to leave along its gradient. And so it's going to leave. We have a bunch of potassiums leaving, and so the cell is going to, it's going to drop and get more negative. And this thing's the gate's starting to close, but it's closing slowly, like it opens slowly. But here, it's like 6, 7. Here at 8, it's completely closed. And this whole time we have potassium leak channels. So also here's potassium leak channels and the voltage potassium channel. And it's letting out all those positive, so it's leaving behind a bunch of negatives, and it's going to get negative, it's going to dip a little bit. When it comes back down, it's called repolarization. But when it dips below the negative 70 RPM, it becomes, what's it called? Hyperpolarization. But then, since this voltage-gated potassium channel closes, it's not going to be so negative anymore. And it just has those potassium leak channels, and so it's going to come back up and level out again at negative 70 RMP. Another kind of important thing from about right here to about right here. This is the absolute refractory period. And that's when the gate for the sodium voltage gate channel closes. Well, I guess it opens, closes, because the inhibitor. And at this point, inhibitor, or I guess the original door finally closes. Then in between here around, the inhibitor resets to back down here. And that's absolute refractory. The reason why that's important is because you can't have another action potential during the absolute refractory period. There's a relative refractory period from like here to here. I guess not completely right there, but it's like before it actually gets back up to leveling off at RMP, 78 RMP. Right there, yes, it can it can do another action potential. But yeah, here number 1 is like sodium, potassium leak channels. Here it's mechanically still whole time potassium leak channels. Right here it's more of those mechanical gated channels. 3, the sodium voltage gated channels opens up. So does the potassium voltage gated channel, but they open at different rates. And so here, sodium door closes. No, sorry, it's still open, but the inhibitor closes down. Also up here, potassium voltage gated channel fully open, starting to close, fully closed here. Around up here is when this thing resets and this door closes. Lastly, real quick, just going to talk about the capacitance and length constant. This is a cell stoma right here. We have the potassium voltage gated channel. It gets set off go through an action potential. We have all these positives that come in from over here. It creates the Wong like we talked about in class. And it's going to move down until it hits another sodium. So when this goes off, it lets in a bunch of sodium, positive, sends that positive electric field down until it hits another one, sets it off again, keeps on going until it moves all the way down the neuron. That's kind of how it works, but there's a couple things that can affect it. Myelin, like we talked about in class, affects this because myelin doesn't allow for the sodium. It doesn't allow for any channels to go in where the myelin is. So where the myelin, it's kind of think of it really smooth, or it has these metal, I don't know, just very smooth. There's nothing really blocking or resisting it. And so through the myelin, it moves a lot more smoothly, and it can move faster, quicker, with less resistance. But also something with the myelin, we're going to talk about capacitance. This is a length constant, by the way. It's these positives that come in to create the Wong. The Wong is a length constant, it's an electrical magnetic field moving down to hit another sodium voltage gated channel to open it up, bring in more positive, creates another Wong length constant. Where it's unmyelated, you have a lot more positives on the outside, a lot more negatives on the inside of the cell membrane, whereas over here, you're gonna have a lot less. So capacitance is measuring, that's what capacitance is. Q would be separation of charges, voltage. So it's measuring the separation of charge with the voltage, and that gives you the capacitance. What I like to think about capacitance as capacity. So these plus charges and these negatives, that's kind of the capacity it's measuring. So over here, where it's unmyelated, there's a lot higher capacitance, there's a lot higher capacity of these positive and negative charges along the membrane. Where it's myelinated, you have a lot less charges along these, and so there's a lot less of a capacitance. There's a lot less capacity of these negatively, positively charges. And I honestly can't remember exactly why there's less along here where the myelin is. I know it's further away, so there's, oh, I remember. Because here, they're so close to each other, they're mainly focusing on being a positive and a negative together, so they're less able to push away a positive charge that wants to come in, so this positive charge can come in easily, attract a negative charge. Over here, they're so far away, they're barely connected to their negative charge. They have a lot more ability to push away any positive charge that comes through, so you have less along that part. So yeah, that's essay number 2. Hope you enjoyed it. Thanks for all who attended today. Thank you, Marissa, my sweet wife who came to support me. But yeah, that's essay video number 2. Thanks for watching. Have a great night.